The power forms are probably my favorite forms to work L'Hopital's rule on because I don't know why, I just like them. Maybe because they're the ones that come up the most often in calculus too. So I'm more common, it's more common for me to work on them. They do generally take the most work because they have to be transformed twice. So they start with 0 to the 0, infinity to the 0, or 1 to the infinity. Remember, the 0 to the 0 and infinity to the 0 come from the definition of the 0th power being take the base and divide it by itself. Well, that leads you to 0 over 0 and infinity over infinity, which are the two basic indeterminate forms. 1 to the infinity is indeterminate for reasons I can't fully explain, except to say that when you take any non-zero number and you multiply it by itself repeatedly, weird things happen at infinity. And so 0 to the infinity is 0 because it's a 0, it has no magnitude. But 1 to the infinity, 1 times itself repeatedly, is not always 1. So we're going to see that it can go to many different values. In fact, this is going to lead to one of the definitions of the Euler's number, the exponential number. So when we have these, we have to first convert them into the arithmetic form 0 times infinity. And then we can convert that form into 0 over 0 and infinity over infinity. Now, how do you suppose we're going to deal with the fact that we have exponents? What have we done in the past? And I believe it was on the last exam where we did something to the expression to get the power down where we could get our hands on it. What did we have to do to it to get our hands on the power?
Use logs.
We used natural log. So we took the natural log of it in order to get the power to the front, and that gives you the product of the original power times the natural log of the base. That's what leads to the 0 times infinity form. That's going to be the original power times the natural log of the base. But the problem is, in a limit, it's not an equation, it's an expression, right? We're not trying to solve an equation, we're trying to evaluate a limit. It's not the same thing. We don't have two sides to take the natural log of. So in order to undo taking the natural log, we raise the whole thing to base e to the power. So we apply the natural log, and then we apply its one-to-one inverse e to a power. And in that sense, we'll undo it, all right? So a word of caution, when we take the natural log and we pull that power to the front, that's going to give us the form of 0 times infinity. Then we have to choose one to move. In this case, it's not a choice. You never move natural log. You always leave natural log in the numerator. You always move the power. So the natural log stays, and you move the power by dividing by the reciprocal. Okay, so let me show you what I mean by taking the natural log and then applying the one-to-one inverse. We want to take the natural log of the function. So you can see that right here where we're taking the natural log of the function, and that pulls the power to the front and multiplies it by the natural log. But because we don't have two sides to apply the natural log to, we have to undo what we've done by taking e and raising it to the power of the natural log of the function. So e to a natural log undoes each other and just gives you back f. So when I have this written, and let me write it larger so that everyone can see it more easily, as x goes to a, e to the natural log of the function of x, where f of x is an exponential, then this becomes basically the limit as x approaches a of f of x. E raised to a natural log power, they're one-to-one functions. When there's nothing between the natural log and the e, they undo each other and you just get the argument to the natural log, which is f of x. So applying the natural log and then applying e to that power undoes what we need to do to get our hands on the power. So let's work through an example. In this example, we're actually going to see what it leads to is something pretty important, pretty special. So we have the limit as x goes to 0 of 1 plus x raised to the 1 over x power. So I'm going to write this a little bit larger. So we have the limit as x goes to 0 of 1 plus x raised to the 1 over x power. So the 1 over x power is applying to the parentheses. We want to really exaggerate the location so you don't make the mistake of thinking it's multiplied by it. It's not a factor, it's a power. First, we substitute 0 in to see what form we've got. So when we substitute 0 in, we get 1 plus 0 to the 1 over 0 power. So when we substitute that in, this 1 plus 0 raised to the 1 over 0 power, 1 over 0, of course, is going to go to infinity. So this becomes 1 to the infinite power. That is one of the 3 indeterminate forms. It's one of the power forms. So we're going to have to apply the natural log to get the power to the front. And to undo that, we'll have to take e and raise it to that power. So first thing we're going to do is we're going to start down here with the original limit, and then we're going to apply e to the natural log of that function. So right here in the second step, you can see that you've applied both the natural log and e to that power. So these are one-to-one inverses. They undo each other. So in essence, you haven't done anything. You're like a dog chasing its tail. You just went in one circle and stopped. Now, because e is a constant and does not depend on x, we're able to pull the limit into the power. This is a very tricky calculus step here. Because e is a constant and doesn't depend on x, we're able to pull that into the power. So now we have e to the limit x goes to 0 of the natural log of 1 plus x raised to the 1 over x. If you were writing this on lined paper, which you should not be, you should be using computer paper, this would have to extend over at least 3.5 or 4 lines. All right, you cannot fit this into 1 or 2 lines. You will not be able to read it and you will make mistakes. So make sure you really exaggerate the locations so that you know the base is e. The power is the limit of the natural log of 1 plus x, which is again raised to a power of 1 over x. Now, we apply the property of natural log to pull the power to the front. So in this step here, we still have e as the base. The limit is still x approaching 0, but now we pull the power to the front and multiply it by the natural log of the original base. So this is the original base, and this was the original power. So we have the power times the natural log of the original base. All right, everybody with me so far?
Why can't we do that? Sorry.
Because e to the x and natural log of x are one-to-one inverses.
Oh yeah, no, I meant the power, like dropping the power.
That's a log property.
A log property?
It is a logarithmic property.
Oh, okay.
All right. So it brings it to the front. So if you don't remember that, come see me during office hours and we'll run through. There are about 7 log properties, and I can run through them really fast and remind you what they are from algebra or college algebra or pre-calculus. You should have seen it before this class, but if you missed it for some reason, come see me and we'll run through the 7 different properties of logs real fast. Okay. So now the next step is I need to evaluate what I have. I evaluated it in the beginning and I got 1 to the infinity. Then I used the e to the natural log to get it into a power so that I could use the natural log property to pull the power out of the power. I had to get the power out of the top and down to the line so I could work with it. Now that I've done that, I need to evaluate what form I have again. So now I'm going to evaluate, and I have e to the limit as x goes to infinity of 1 over 0 times the natural log of 1 plus 0. 1 over 0 goes to infinity, and the natural log of 1 is 0. Does everybody see that that leads to the form of infinity times 0 or 0 times infinity? This is one of my indeterminate arithmetic forms. I expected this. This is going to happen each time. I expect that I'm going to get something that's arithmetic of the form 0 times infinity or infinity times 0. Now I need to do something to convert this into a fraction. You will never, ever move natural log. Natural log will always remain in the numerator. So that means that the power part has to fit somehow in the denominator. In this problem, it's pretty easy. What I would do would be just slide the x underneath. Now you can also divide by the reciprocal of 1 over x, which is still going to give you the same thing. I would instead write it like this: e to the limit as x approaches 0 of the natural log of 1 plus x divided by x. In other words, you've got 1 over x times the natural log, just slide the x underneath. And now you've got a fraction. Well, once you have a fraction, you need to reevaluate again. So now that we have a fraction, we need to reevaluate. So we have e, limit x is going to 0. We have the natural log of 1 plus 0 divided by 0. Now the natural log of 1 is 0. So I have e to the limit of 0 over 0. And again, I'm not looking at the base e, I'm looking at the limit value, and the limit value is going to 0 over 0. So that's one of my indeterminate basic forms. So now I can apply L'Hopital's rule to this expression right here. Natural log is always in the numerator. I don't get to say always very much, but it really pleases me to give you a rule that never fails. Natural log always stays on top. Now we're going to apply L'Hopital's rule. So when we apply L'Hopital's rule, we put the L apostrophe H. So let me recopy what we have so that you can see it. And I'll put it right here below where the words are. So we have e to the limit as x goes to 0 of the natural log of 1 plus x divided by x, which we saw led to 0 over 0, actually e to that. And the 0 over 0 is a basic form for the limit. So we're going to apply L'Hopital's rule. So we put L apostrophe H, e to the power, which is the limit, just keeps following along. The e is just tracks, right? Some students don't write the e, they wait until the end and then put the e back in, which is okay as long as you don't forget it. You have to remember that the base is always there. What's the derivative of natural log? How do we take the derivative of natural log?
Is it 1 over the derivative of the inside times the natural log of e, which is 1 times in the chain rule?
Yes, so
Yeah.
we're going to use the chain rule. So it's 1 over u, 1 over the argument to natural log times derivative of the argument. So we're going to get 1 over 1 plus x, freeze the inside, times the derivative of 1 plus x. That's chain rule. All divided by, and I'm running out of space, 1. Notice how when we do L'Hopital's rule, it starts creeping down towards where the e is, which it really shouldn't because it's power. So in that sense, you may even need to take up 5 or 6 lines of space. So let's do a little bit more algebra to clean this up. So we have e to the limit, x goes to 0. I've got the derivative of 1 plus x is 1. So I've got 1 over 1 plus x. And then when I divide by 1, it doesn't change it. So I essentially have the limit of 1 over 1 plus x. Now I need to substitute it in again. When I substitute it in, I'm going to get e raised to the power 1 over 1 plus 0, which becomes e to the 1 over 1, which is e. You have just discovered another one of the definitions of e. This is one of the definitions of e. So the limit as x goes to 0 of 1 plus x to the 1 over x is equal to Euler's number e, which is about 2.71828182845.9, and I lost it from there. It is an irrational number like pi. It is the natural base for exponentials. So it describes exponential situations really, really well. Things like population growth, the spread of disease, the decay of radioactive material, bacterial growth, all those kinds of things. All right, the spread of rumors and gossip, it describes that as well. Okay, let's apply this process to example 17. We have the limit as x approaches 0 of 1 plus 4x to the 3 over x. So first step, plug in, see what form you have. If you get a finite real number, you're done. So I'm going to plug it in, and I get 1 plus 4 times 0, all raised to the 3 divided by 0 power. That's going to give me 1 raised to the infinite power, which is one of the 3 power indeterminate forms. So now I'm going to take this and I'm going to apply e as the base, and then I'm going to do natural log, and I'm going to pull the limit up into here eventually. So I have the limit of e natural log of 1 plus 4x to the 3 divided by x, right? So I apply the natural log, and then I undo it by taking e to that power. So I, in effect, mathematically haven't done anything, all right? But then I'd use the natural log rules to bring 3 over x to the front. So I'm going to take this 3 over x, and I'm going to bring it to the front of the natural log.
Can you repeat those 2 steps? We're applying the natural log, and then the function or the operation that undoes it
Yes.
is what?
Oops. All right. So natural log will allow us to bring the power to the front. The inverse operation, the undo operation for natural log, is taking e and raising it to that power. So just like multiplication and division are inverse operations, multiply by 3, divide by 3. What have you done? Nothing. So in that sense, applying the natural log and then taking e to that power, you've done nothing. It's the same thing as applying multiply by 3, then divide by 3. Or add 5, now subtract 5. You've essentially done nothing, all right? So that's what this does, the same thing. Now, because e is a constant and doesn't depend on x, I'm allowed to pull the limit up into the power. And I need to evaluate what I have here in the power now that I've pulled the power down to the line. So when I evaluate, I get 3 over 0 times the natural log of 1 plus 4 times 0, which gives me infinity times the natural log of 1, which is infinity times 0. So in my next step, I'm going to pull the limit into the power. So e is the base. I have the limit as x goes to 0. And I need to rewrite this in a fractional form so that I can evaluate it and get one of the two basics, 0 over 0 or infinity over infinity. Either one will work. Natural log never moves. It always stays in the numerator. The obvious thing to do is to slide the x in the denominator underneath the whole thing and to write it as 3 times the natural log of 1 plus 4x all divided by x. That puts it in fractional form. And now I need to evaluate it again. So I'm going to substitute in the value x equals 0 again. So this is going to give me 3 natural log of 1 plus 4 times 0 over 0, which is 3 times the natural log of 1 over 0, which is 0 over 0. Actually, it's e raised to that power. But the limit is in the power, so the form of the limit is 0 over 0, so we can apply L'Hopital's rule. So now we're going to apply L'Hopital's rule. The 3 is a constant. The 3 could be brought out of the entire limit and put in front of the limit if you want, or you can just leave it tagging along as a coefficient. The derivative of natural log is 1 over u, 1 over 1 plus 4x, times the derivative of 1 plus 4x. So this is going to give us base e, limit as x goes to 0, 3 is a coefficient tagging along, times 1 over 1 plus 4x times the derivative of 1 plus 4x, which is 4. And I'm going to write it out in a couple steps just to remind you of the chain rule. All divided by the derivative of x, which is 1. This is L'Hopital's rule. Now let's clean that up and do the derivative of the inside function. So we have e limit x goes to 0. The derivative of 1 plus 4x is 4. So I have a 3 times 4 over 1 plus 4x all over 1, which becomes e to the limit, x is going to 0, of 12 over 1 plus 4x, which is as simple as I can write it. Now that I've done the algebra to simplify, I'm going to substitute the value of 0 in again. So this is going to give me e to the 12 divided by 1 plus 4 times 0, which is e to the 12 divided by 1 plus 0, which is e to the 12. And that's the final answer to that one. I think sometimes the 1 to the infinity ones are the hardest. They tend to have more in the argument to natural log, so they tend to be a little bit more difficult. We now want to look at one of the other forms. So we're going to look at this one. The limit as x goes to 0 of x to the x power, which is a tower function, t as in Tom. Tower functions are variable bases raised to variable powers. They're the fastest growing functions we have. So we're going to substitute the value of x in, and I have 0 to the 0, which is automatically one of my indeterminate power forms. So then I'm going to apply the natural log to get the power out, and then the undo, which is e to that power. So I have the limit as x goes to 0 of e to the natural log of x to the x power. I'm going to apply the logarithmic properties to pull the power on the base to the front as a factor. And then I'm going to pull the limit up into the power. So I have e to the power limit as x goes to 0 x times natural log of x. Now we want to evaluate it again by substituting in the 0. So we get 0 times the natural log of 0. Now, natural log of 0 is not defined, so you need to think in terms of the graph. What does the graph of natural log of x look like? As x approaches 0, we see that the natural log function approaches negative infinity. So this becomes 0 times negative infinity. Any form of infinity works in the 0 times form for an indeterminate. So we have a 0 times infinity form, which means that we need to write this in fractional form. Natural log always stays in the numerator. So I have to move the x. This time it's not obvious. I can't just slide it under the denominator. It's multiplied by the numerator. So instead, I'm going to have to apply that trick of dividing by the reciprocal. So multiplying by x is the same thing as dividing by 1 over x. All right? The denominator of the denominator goes in the numerator. So this is the same thing as x times natural log of x. Now that I've done something, I want to substitute the value in again because I need to have a basic form before I can do L'Hopital's rule. So I plug in 0. I get natural log of 0 over 1 over 0. I know natural log of 0 is approaching negative infinity, and 1 over 0 approaches infinity. This means I have one of the infinity over infinity indeterminate forms. I can do L'Hopital's rule. So now I'm going to do L'Hopital's rule. E is still the base. Limit is still in the power. The derivative of natural log of x becomes 1 over x. The derivative of 1 over x is negative 1 over x squared. Right? Now I need to clean this up and do some algebra to simplify it because it's looking kind of complicated. So I have E as the base, limit in the power as x goes to 0. I'm going to remember that the denominator of the denominator moves to the numerator. So that's x squared over x, and I still have a negative. All right, the bottom of the bottom is the top. The top of the top and the bottom of the bottom are on the top, and the bottom of the top and the top of the bottom are on the bottom. All right. So again, if top, 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 bottom, 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 but top again, sorry. Top, I can't say it. Bottom of the top, bottom, top of the bottom, bottom. If you have a mixture, it goes in the denominator. If they're numerator of the numerator, it's in the numerator. Denominator of the denominator, it's in the numerator. All right, if they're the same. Now I can reduce that. That gives me e to the limit as x goes to 0 of negative x. Now I can substitute in again, and this is going to give me e to the negative 0, which is just e to the 0, which is the number 1. So it approaches 1. I think those are easier than the 1 to the infinity forms. Okay, now we want to look at one that's a little bit different and involves some trigonometry. So we want to take a look at this one. It is one of the power forms because it is sine x raised to the tangent of x power. So the first thing we want to do is make sure that it is an indeterminate form by substituting in what x is approaching, which is 0. So I have sine of 0 raised to the tangent of 0 power. Sine of 0 is 0, tangent of 0 is 0. I have 0 to the 0, which is an indeterminate form. Now I'm going to apply the e to the natural log technique. So I have the limit as x goes to 0 of base e to the natural log of sine of x, all raised to the tangent of x power. Then I'm going to use the logarithmic properties to bring tangent to the front, and I'm going to pull the limit up into the power. So e is still my base. Pull the limit into the power. Pull the power down to the line so you can get your hands on it. I would put tangent of x in parentheses times the natural log of sine of x, which I might put that in parentheses too, to emphasize that it's the argument to natural log. Now that I've applied the technique to convert it from 0 to the 0 power form, I need to check what form I have. So I'm going to substitute in again. So I have e as the base. The limit itself, though, is tangent of 0 quantity times natural log of the sine of 0. Now, tangent of 0 is 0. Sine of 0 is also 0. But I need to think about what the natural log looks like. So I'm going to think about the function over here. Natural log as you approach x equals 0, which is, of course, the y-axis, it approaches, it's coming down here and approaching negative infinity. So this becomes e, and the limit is being evaluated on 0 times negative infinity. So we have that.
I think we just lost audio.
Yeah.
possibly.
Yeah.
Sorry about that. I accidentally hit my recorder. Okay, so we have e to the 0 times negative infinity. So we're going to have to do something to convert it into one of the two basic forms. Now, this time it's a little bit trickier. Natural log cannot move, period. So I am going to have to divide by the reciprocal of tangent. So there's no other choice. You're going to have to do it, but we will be able to simplify it a little bit. So we've got the natural log of the sine of x divided by 1 over tangent of x, right? So we're dividing by the reciprocal of tangent, which is 1 over tangent. Now we need to check our form again. So we have e to the natural log of the sine of 0 over 1 over the tangent of 0. The sine of 0 is 0, so we have the natural log of 0. The tangent of 0 is 0, so we have 1 over 0. Natural log as it approaches 0 goes to negative infinity. So we have e to the negative infinity. 1 over 0 also approaches infinity. The numerator is fixed and the denominator is approaching 0, so it goes to infinity. So we do have for the limit the indeterminate form 0 over or infinity over infinity. So we can apply L'Hopital's rule. Now, you can do it whichever way you want. I might consider, because this is 1 over tangent, before I do L'Hopital's rule, I would probably rewrite this in terms of cotangent, which would make my derivative easier. So I have natural log of the sine of x over cotangent of x. Right? Now I can do L'Hopital's rule. And this is going to be e limit as x goes to 0. And we have the natural log of sine of x. The derivative of natural log is 1 over u, which is sine of x, times the derivative of u, which would be cosine of x. Don't get excited. You have to take the derivative of cotangent. So the derivative of cotangent is, it's a cofunction, so it's negative. And the derivative of cotangent is negative cosecant squared. All right. Now I need to do some algebra to clean this up. So I'm going to rewrite this in terms of sine and cosine. So I have e to the limit as x goes to 0 of cosine of x over sine of x over -1 over sine squared of x. Remember, cosecant is the reciprocal of sine. So I'm using algebra and trigonometry to rewrite this. And then remember what we just said before, the denominator of the denominator is in the numerator. The denominator of the numerator goes to the denominator. So when I rearrange this complex fraction, I get e to the limit as x goes to 0. Cosine x is in the numerator times sine squared of x is in the numerator. In the denominator, I have the -1 and I have sine x. Now, one of the sine x's will cancel the other sine x that's in the numerator. And that leaves me with e to the limit as x approaches 0 of negative cosine of x times sine of x. And then I'm going to substitute my value in again because I've done as much as I can do to simplify it algebraically. So I'm going to substitute the value in again. And this is going to give me e to the negative cosine of 0 times the sine of 0, which becomes e to the -1 times 0, which is e to the 0, which is 1. It almost seems kind of unfair that after all that work, you just get 1 for the answer. You've done this tremendous amount of work. You should get some really spectacular number, but no, it's just 1. All right. The only other thing that we have to talk about are the growth rates of functions, the general growth rates of functions. And the symbol we use for that is this double less than to show an order of magnitude of difference on the growth to infinity. So in this example right here, you'll see the general growth rate of functions. So if you're trying to decide which type of function overpowers another, natural log grows slower than anything else, on an order of magnitude slower than natural log times any algebraic function. Remember, algebraic is add, subtract, multiply, divide, raise to a power, and take radicals. So basically, your polynomials, your rationals, and your radical functions are algebraic, which is an order of magnitude slower than algebraic functions, which is an order of magnitude slower than algebraic times exponentials. The algebraic slows it down a little bit. Pure exponentials grow the next fastest. Then factorials, if you've not seen those yet, don't worry, they're coming. And then tower functions are the fastest growing class of functions that we have. And this is what's called the relative growth theorem. It is not covered in your textbook, but it is covered in some textbooks, and it is definitely very useful in the future for deciding what order of magnitude and what outweighs what. So if you're comparing an exponential to a natural log, the exponential is going to win and pull it towards that direction. If you're comparing a natural log with some kind of polynomial or radical function, the polynomial or radical function is going to overpower the natural log and pull it in that direction. Right? So this is the end of this section on L'Hopital's rule. And next time we'll be talking about antiderivatives.